Hi, today I want to get the build back out and work on the things I need to do to extend the flags register into the control module so I can handle conditional instructions. There's a couple of things I need to do as prerequisites to that, and by the end of this video I want to have the flags extended so that I can evaluate and handle conditional instructions. There's some timing concerns with that as well. It's not a light lift here, so let's get into it. Hi, my name is Adam. I'm building a 16-bit computer from scratch. I hope you'll join me on this journey. So when facing a complicated problem, I always find it best to start with a definition of what I need to do. In this case, I'm going to break it down into a few different steps, and we'll take them one at a time. The first step here is going to be to change the instruction suppress to use an OR gate. Now, currently the next instruction is suppressed when the instruction itself contains an immediate value which comes next in the instruction stream. And so when that happens, when the instruction requires that the next word in the instruction stream does not go into the instruction register, but rather is to be asserted someplace else, there's an instruction suppress signal that gets asserted. This comes from the control logic. Now I'm going to have a second source for that signal, which is going to come from the condition evaluation. And I want to make sure that either of those will properly suppress the instruction. And so, as I mentioned here, we'll need it shortly. But it also introduces a new signal delay that I have to look at and take into account. And before I get too deep into this, and I have no idea how this is going to turn out, what I want to do is I want to set up that delay, change it so that it is ORed with 0, which it just becomes a buffer at that point, and do some tests and make sure that my existing code still works when I'm loading constants. And so let's get that done first. Okay, I'm zoomed down pretty closely on this side of the board, and then over here I've got the code that I'm using for the control module. I'm going to use that for deciphering exactly what signals I have coming from where. Now my instruction suppress is down here in my control signals for my fetch register, and it's this third bit here, the third bit along. The signal for that is right up here. Of course, it's popping out of the breadboard, which comes from up here, control 1, and it appears to be 1, 2, 3, 4, 5. So bit 4, 0. This would be 0, bit 1, bit 2, bit 3, and bit 4 is right there. So coming over to my code that I can refer back to that, coming off of control module 1, bit 4, yes, is my instruction suppress. When it's 1, I am suppressing that instruction. When it's 0, I am asserting that instruction from the fetch register up into the instruction register a little bit farther up. So now what I need to do is I need to put an OR gate here and take that same signal, run it over here, run it through the OR gate, ORed with 0 for now, because there's a second signal that's going to come in, but I don't have that yet, and then run that down into this spot. Let me get that wired up. Okay, so I chose to use this lower left OR gate here. Input 1 is coming off of the signal that was being transferred down here before. Input 2 is tied low for the moment, and then the output here now comes back to where the original signal was. Let's give it a test. Okay, I've zoomed quite a ways back out again so you can see everything. I still have in my program ROMs the latest jump test that I did from video 51. And that is the test that confirms that the jump instruction is actually properly flushing the fetch register and fetching the correct instruction after the jump. So that said, let's get this plugged in and let's step through this code real quick and make sure that when I do load an instruction, it actually suppresses properly here. So let me reset this down, make sure everything is clear. First instruction is here, gets loaded into the fetch register. This is the value that's going to be loaded into my R1 register, and that worked. When the instruction went up here, the value is here. Now when I fetch again, I get my instruction here, but nothing moved up into the instruction register, and that is the correct behavior. Now you saw me pause a little bit because when I release, I'm pushing the clock button down now, so the clock is high. When I release it, that's when it latches, and I had to remind myself of that in my head. So this is working the way I believe it should, and if I speed this up just a hair, you can see the value crawl all the way across. I get to the end, and I jump back to the start, which is exactly what I wanted to see. And I only see one jump instruction move through there. Okay, so that test is successful. Speed that up a little bit. It's not capturing it really well with frame rate of the video. It's about as fast as I think I can get it to go. But you can see I'm only getting one flash over here, so I'm only getting one jump instruction. So that now brings me to where my concerns are here with getting the ALU right in the timing. Let me see if I can lay this out in a way that makes some sense. Let's assume that in the instruction register there is an instruction that requires the ALU. Let's just say add R1 to R2 and store the result back in R1. And then conditionally in the fetch register is another instruction, doesn't matter what it is, but it is predicated on the results of the flags of the instruction that take place in the instruction register. Looking at that instruction that's in the instruction register, ALU A and ALU B are asserted during the entire clock cycle, and we can see that down here with the other bus asserts. We're asserting onto those buses during the entire clock cycle. The ALU performs its function during the high clock cycle, so while the clock is up here. And then on the falling edge of the clock, everything gets latched. So here we've got the latch back in R1, and we'll need to latch the flags at that point as well. I don't believe it's going to be appropriate to hold off on latching those flags because the contents of what's being asserted out onto the bus are likely to change as a result of that. So that latch actually has to take place at the same time that the result is latched. Ultimately, the question is this enough time? And I am not certain it is. Because not only does the ALU have to handle receiving the data, performing the operation, calculating the results and the flags that go with them so that they can be latched on the falling edge of the clock here. It just seems very aggressive to me. Now, the slow clock speeds that I'm dealing with now with the breadboard, that's not going to be a big deal. But once I get to the higher clock speeds that I'm hoping to get to, once I get to the PCBs, that's when I'm going to be able to determine just how fast I can run this computer. The flag evaluation itself is going to have to take place on the low edge of the clock. So down here, that's when we're going to evaluate whether or not the next instruction is going to take place. And that may seem a little aggressive, but it's the period in time that I have in order to determine, because on the rising edge of the clock is when I latch the fetch and instruction register. So if I'm going to do an instruction suppress, I have to make that decision ahead of that rising edge. So the instruction suppress has to be asserted from the fetch register. So let's assume for a moment I'm moving a constant into register R1. And moreover, that constant happens to be a value such that it looks like it should be a conditioned instruction. But it's really not, it's just a constant value. Well, I'm going to be okay there because the constant is never actually going to make it up into the instruction register. The instruction itself is such that it's going to suppress the movement of that constant into the instruction register and replace it with a no-op. So regardless of whether that evaluation turns true or false, that constant is never going to be interpreted as an instruction and make it up into the instruction register. But regardless, the instruction or no op has to be latched on the rising edge. So I only have a half of a clock cycle to determine the results and a half of a clock cycle in order to determine what the next instruction is going to be. So at this point, it makes some sense to take a look at exactly how I plan to integrate this into the control logic. And here is the ALU output that I have done so far. And then I've added some LEDs up here just for my own sanity so I can keep track of exactly what's going on here as I test this out. So I'm going to add a latch register, and I need to latch the flags for timing purposes, and I need to make sure that I latch all the conditions associated with the flags. Now you're probably going to ask, Adam, you're already latching the individual flags in the flags register itself. Why do you need to latch them again? And the answer to that is simply because of timing. Because I have to latch the flags on the falling edge of the clock cycle with everything else associated with the ALU calculation, but the movement of the instruction takes place on the rising edge of the clock cycle, I need that half clock cycle delay where things may be changing to change what the result of the previous flags are. Now the 74HC151, that is a multiplexer where the conditional inputs 1, 2, and 3 are going to select which output off the latch is going to be selected out onto the pin. And I'm going to take the inverted version of that pin and use an exclusive OR with condition bit 0. And that should give me the results that I'm looking for. This LED here is a instruction suppress LED. And what I may end up doing is I could end up dropping in an inverter here, which indicates now that if I am going to execute the instruction, the LED is on. If I'm going to not execute the instruction, the LED is turned off. That just cleans up the logic a little bit to make sure that it makes a little bit more sense. The 1 bit for the instruction suppress is what's going to be ORed with the instruction suppress coming off the control logic. So this is ultimately what I intend to use to incorporate into my control logic. But I also see a bit of a problem here. Let me explain. Now I want to let you in on a little bit of inside baseball here. I don't record these videos in one sitting, and I will actually record a segment and then edit that segment and then turn around and record another segment and then edit that segment and then record another segment. You get the picture there. In between recording segments, my brain doesn't turn off. And so I end up thinking my way through several of these things and come up with issues that I need to consider. That's actually what's happened here between the start of recording this video and this point in time. What I have realized is that there's a problem that I did not take into account. And it comes at me randomly, but I don't ever stop thinking about it. So as I set out to do this video, was completely different than how I expected to end up. So let me illustrate that. So I managed to come up with 4 different conditions that I want to be able to test, and all the different possible combinations result in 16 different permutations of tests. I've got each of those test cases out on the right hand column. Now the ones that are highlighted in blue actually are 4 instructions, not just 3. And the reason there's a 4th is I actually have to make sure that my test case is set up perfectly. So I am going to set the carry flag and then do a 2-byte instruction ahead of the conditional instruction move when carry is set. A couple of other things related here. I am going to have to implement a couple additional instructions. Clear carry and set carry are going to persist. But there's also this move of the program counter into R1, which is what I have available to me at the time. It's not going to persist. I just need some type of a 2-byte move or 2-byte instruction really that is different than a jump instruction so that I can determine if things are working properly or not. Now, that said, I believe that there are going to be problems with a couple of these test cases. Specifically, there's 4 that are highlighted here. And these are the ones that have 2 conditional instructions, or 2-byte conditional instruction where the condition is not met and therefore the instruction should not be executed. I really didn't think about this when I was considering the instructions. I was considering when the condition was met and the instruction should be executed. But when the condition is not met and the instruction should not be executed, I was only going to set the instruction register suppress control, and that would suppress the first instruction word into the instruction register, but the second instruction word would actually be moved up into the instruction register and executed as if it was an instruction, and that, I believe, is a big deal. Now I'm going to go through and I'm going to test this just to make sure that my thinking is correct, but I want to call out right from the get-go that I do expect problems with this, and I actually do have a backup plan for it. Once I confirm that this does not work the way that I need it to, I will illustrate what my solution is for this. Okay, I've got my flags build back out, and I want to start by hooking up the latch and get that all integrated here. I'll stick up in the corner up there a copy of what the CircuitVerse drawing is that I'm going to test here. And again, I'm not expecting this to work. If you caught my last segment, there's going to be a flaw here, I believe, and so we'll end up discovering that and working on that together. Like I said previously, I do have a plan to solve that. Let me get this wired up, and I am following the diagram in the corner up there. Pin 1 is output enable, and then pin 2 is tied high. And then some quick hookups here. 3 is tied to the Z flag, so 3 tied to the Z flag. The Z flag is this bit 7 over here, so I'll take it from there. Pin 4 is tied to the C flag, 4. Pin 5 is tied to the N flag. Pin 6 is tied to the V flag, so those are all in order, so that's good. Pin 7 has to go through an AND gate, so there will be the AND gate, and its 2 inputs are the C flag and the inverted Z flag. So the C flag here is input number 1. Straighten that pin out. And the inverted Z flag is this one. That was pin 7. Pin 8 is the inverted L flag. That's going to be this one. And then pin 9 is also coming off the output of an AND gate. And the 2 inputs for the AND gate are the inverted L flag and the inverted Z flag. And I'm going to spend a minute cleaning those up. Okay, now let's get a look at the multiplexer. Okay, here's the multiplexer. I'm going to drop that in right here, and I'll go ahead and decouple it real quick as long as I've got what I need here. The output that I'm going to take is the inverted output, which is W. W is pin 6. So this is the one that's going to end up coming over here. I'll just go ahead and tie it to an LED for the moment. Let me get power and ground. And then I've also got an enable line, which is pin 7, which also needs to be pulled low. D0 is pin 4, which is my data component 0 or choice 0, data choice 1. And then it wraps around the IC to the other side, skipping VCC, of course. Now my latch also needs a clock, which I'm going to just bring that over here just so I don't forget it. And then I've got A, B, C, A being the least significant bit, B being the next one up, and C being the most significant bit. That's going to be the most significant bit of my 4 bits to select which one. And then my genuinely least significant bit is going to be here, and that'll be landed over here someplace. I will need to take that to the XOR gate over here somewhere. But this now gives me a place to land my control signals in. Let me clean up this wiring a little bit. So now I have to create a 4-pin ribbon cable for taking this signal from the control module. My output has to be exclusively ORed with this signal, and I'm going to have to do that on this side of the board. And then I'm going to have to pull clock in from the control module as well. I'm wondering if it doesn't make sense to include clock in this bundle. I don't have the board in front of me. I'll have to look. Finally, here's the exclusive OR that I'm going to use to condition that signal whether or not it's supposed to be inverted or not. Let me get the decoupling in here real quick, and then power and ground. And these are my 2 inputs here. And my output now becomes this pin right here. This is my instruction suppress signal. Is that correct? It is not correct. This is clock here. Let me get a better wire here. This now becomes my instruction suppress. So this is the inverted output off of the multiplexer here that goes into one side of the exclusive OR. My least significant bit of my 4-bit condition becomes the other half of the exclusive OR. And then this is my output, which is now going back off board. Let me clean up those. Now we should be able to get the build out and give this a test. Okay, I've got the full build out now, and I've attached the flags down here in the bottom corner. And the first order of business is to get power and ground hooked up, and then I need to get some decoupling caps in here as well. Okay, I'm just going to go for the quick hookup here. this was my clock that I need to tie back over here. This one is my instruction suppress. That instruction suppress needs to be tied. I'm looking for a longer wire here. Let's see if I can find something. Needs to be tied to the other side of this OR gate, and then at the same time this pull down comes out. I need 4 lines hooked up over here. These need to be coming from the instruction. So I believe they are 1. I'm going to hop them here. That should be my integration hooked up. Now, if I look at some of the changes I had to make for the code, I also have a few things I need to get hooked up down here. So clear carry is going to come off of here. That's going to be latch 0, 1, 2, 3. And again, I'm going to have to hop them. Yeah, I can't get all the way down there. And then 2, which is set carry. Clear carry, let's see, I'll stick this here. Clear carry is the farthest to the left. And then set carry is the next one over, which sits there, because I didn't make them lined up right. I also added a PC assert main, so I need to tie the program counter, which is bit 15 up here. I believe it's that one. And this has to come down to my main and then eliminate that connector. Sorry about hitting the microphone. Let's check that pinning. Yeah, that's correct. So that allows me to assert the program counter out onto the main bus. Now I'm trying to think this through, and I think that's all the wiring I need to do to execute the test. Now here's what I've done. I've added a clear carry instruction, a set carry instruction, and this temporary move the program counter into R1 instruction, which I need for testing. In the architecture file, I added the clear carry instruction and the set carry instruction, and the move into R1 the contents of the program counter. Again, that's going to be temporary. It will go away. And then I created a test. Now, this test, I went straight for one of the tests that I expected to give me problems. So this is setting the carry flag, move as long as carry is clear, into R1 the contents, or the value actually, 0013. Now, this is chosen very carefully because this value 0013 happens to be move into R1 some immediate value. And so if that was going to execute, I would get the clear carry instruction as the immediate value moving into R1. And then I've got a couple of no ops and a jump back to the beginning so I can run that test again several times if I need to. I haven't done any of this. I need to program the controls. I have to program my program ROMs over here and give it a test. So let me get those programmed and I'll come back and we'll try the test together. Okay, I've got my logic probe out just because there's a lot of change here that has not been tested, and I have a feeling I'm going to have a couple of issues to track down here. Let me see if I can get this centered up a little bit better. Let's put power in it, and I am on single step, so that's good. Reset, and then is that not back to 0? Okay, step 1, nothing is there. So I am not fetching anything. Let's make sure I don't have anything silly like power disconnected on this ROM. That would make a lot of sense as to why things weren't working. All right, let's try that again. All right, so first instruction, and that's going to be 1, 2. That's going to be 3. First operation is set carry, and I haven't cleared. Okay, so there's the problem. I need to get some form of an inverter in here, so I need to get that cleaned up. Let me work on that. Okay, let's try resetting this. Okay, I'm also going to fast forward through this segment where I'm troubleshooting and deciphering some issues with my control signals. Turns out I had one that I had totally missed and therefore was being incorrectly set, so I had to sort that out. So I have high showing up here, and this is the line driver, so I think I've got this wired up wrong. Well, hang on. No, that's correct. So that's high, that's low, so it should be coming out of this one, which means that my Z select here is here, which is not what it should be. I've got something not right here. It's almost like I've missed a signal. There we go. Let's try that. That's high. That's high. All right, let's try that again. This one's not used. That's 0, that's carry, so that's good. Here's my conditional jump, but it fetched. Okay, the first order of business is to stop trying to think my way through this and go back to the signal map that I had put together for this, and the flags latch is currently the entire clock cycle the way I have it set up. And while I did send it through an inverter to get the signal correct, what I should have done is I should have put it through the inverter plus an AND gate to get the timing right. So let me work on getting that piece cleaned up the way it's supposed to look. Okay, so for the moment, I'm going to land my NAND gate here. And I'll go ahead and put a decoupling cap on that. And then my inverter will land here. And again, I will decouple that. And then let me get this all wired up. Okay, so let me plug this in, perform the reset, clear this. What I should do is tie that into the reset. Let me come back here to my application here. That looks reasonable to me, by the way. So I've got the probe hooked up again. I've reset. And the signal I'm looking for here is low. My clock right now is floating. Okay, am I not getting, do I not have connectivity on that? I have a bad wire. Good God, like I'm fighting all kinds of things here. Okay, so this is high. That'll work because it's locked on the rising edge. Now, at this point, my 0 carry should be high. 0 and carry. And that should latch. Okay, I'm not getting a good clock here. It's because I'm in the wrong signal. Okay, I'm getting that latched right. Try to reverse these. So this one goes to here, so that should be high. Low, high, low. That should be 2. So 0, 1, 2. That's high. And then we're looking for not high. So if that's the case, what comes out of here should be high, which means that I've got an instruction suppress here. And I do have an instruction suppress here. So I should not be asserting here, which means that when I clock, I get a no op, which is correct. And then when I clock again, this is the problem that I am anticipating I'm going to have. So ultimately what this will do is this should move this value into this register, and since it's already there, it's going to do that. So that's the problem. That was the problem I was anticipating I was going to have, and that's the problem I do have. So what's the solution? So the solution here is to make use of this condition met pin on the address lookup into the control EEPROM. I did have this earmarked for this purpose and had intended to use it at one point, thought I might be able to get cute and get away with it in hardware, but no, it turns out that it really truly does need to be managed in firmware in the control logic EEPROM. So the way I have it set up is that 0 means that the instruction has been met, and that seems very natural to continue to execute the instruction based on the fact that the flag has not been set. And then 1 meaning that the condition has not been met, and therefore I should be suppressing the instruction. Now, the only thing that I don't like about this solution is that the instruction itself will still display in the instruction register. And I am likely to try to extend the hardware, the wirings, in such a way that I can suppress the display of that instruction in the instruction register when it's not actually doing anything. So I had a plan originally. I thought I could get cute. Turns out I can't. So we'll go with the original plan. Well, of course, the best laid plans. I had a plan when I started out this video. It got tossed aside. So now all the rest of the videos that I had planned after this need to be resorted, and I got to come up with a plan now for those. I do know that the next video, though, I do have something that I do need to address here before it gets out of control, and I will be doing that next video. And then I need to circle back around to this topic immediately after that and get the conditional instructions built into the firmware in such a way that I can actually test that out, prove it, and then start building out some instructions. I also need an instruction register to be soldered up, so I'm kind of feeling the pressure here to get some things done. So I want to make sure that I'm doing these in a good order that makes some logical sense, but I do have a problem that I've got to deal with first. So that will be the next video, and look forward to that. Thank you. We'll see you soon.